All right, this is a pretty standard example of using the Bernoulli equation. Just comes up in a few contexts, and this is one that you often see. So here we just have some wind blowing like horizontally across the building, and the problem says find the upward force on the roof. So the first thing is conceptually to get why there would be an upward force. The whole idea with this Bernoulli effect is that where you have fast moving air, you want to associate that with low pressure. So inside the building where presumably the wind's not blowing, there should be higher pressure there because you have slower air and you've got this air moving across the top. So there should in fact be low pressure above the roof and high pressure below. So that should actually tend to push the roof up. And so that's one way in which buildings can get damaged in a windstorm. Well, so diving into this, we want to actually figure out how much upward force there is. What we need to do first is use this Bernoulli equation to figure out what the pressure difference is. And so first we'll just write down the Bernoulli equation. And if you remember with the Bernoulli equation, you think of two locations, location 1 and location 2. So you have a pressure term plus rho g times the position 1 plus 1/2 rho v1 squared. So these three, the sum of these three terms needs to be a constant. So the sum of those three terms at position 1 needs to be the sum of those three terms at a position 2. Plus rho g y2 plus 1/2 rho v2 squared. Okay, so a wise choice in this case would be to pick a position, say, just below the roof. So just so that we can see it, I'm gonna sort of draw it under there. Position 1 would be like just below, and position 2 we'll make just above the roof. So just below the roof and just above the roof. So the idea here is that, well, let's say position 2 is up above the roof. So for example, this term here, we happen to know the speed of the air at that place. And so what we can do is we can say, okay, well, you have the pressure inside plus, now what we're going to do is we're going to say that we're just above the roof and just below the roof. So we're going to have the pressure difference because of the height basically go to 0. We're going to say that position 1 and position 2 are effectively the same height because we're just below and just above the roof. Okay. If you wanted to keep those terms, you're saying that the pressure difference due to height just outside of a roof and just inside is important. But these, so since y1 is about equal to y2, we're going to neglect those two terms. And then also presumably in the building, the air shouldn't really be moving around in there. There shouldn't be much wind in there. So since V1 is pretty much 0, we're going to kill that term also. So then you really just have these terms left. So let me just get rid of that. We'll say on the left-hand side, the only survivor really is P1. And on the right-hand side, you have P2 plus 1/2. Now, rho is the density of the fluid. And in this case, the fluid is air. So in general, you'd be given such a thing. And so the density of air under kind of standard conditions, obviously it depends on pressure and temperature and so on, but the density of air is about 1.25 kilograms per every cubic meter of air. And so we'll just plug that number in. So 1.25. And then the velocity was given to be 30 meters per second. So it must be some kind of a crazy storm. So 30 squared. And so what we can do then is if you move the P2 over, you get P1 minus P2, which is really the pressure difference, is going to be 1/2 of 1.25 times 30 squared. So 0.5 times 1.25 times 900 is 562.5. 562.5. And then that's pascals or newtons per square meter. Right, so now what we want to do to find the upward force, well, this is the amount by which the pressure below the roof is greater than the pressure above. And so now we can just say that pressure is force per area. Well, so what area do we want to look at? Well, it's just the roof. So just this top part here. So that's going to be the relevant area. And so what we can do is say, well, we have 562.5 newtons per meter squared applied over, and then the area of this roof, well, the dimension we want really is 5 by 10. So times 50 meters squared. And then that's going to give us the upward force. So 562.5 times 50, that's 28,125. 125 newtons. And then, you know, very, very roughly speaking, a newton is like a quarter pound. So if you roughly divide that, you know, by 4, you know, you get 7,000 pounds-ish of upward force. So hopefully the fasteners and the nails and so on are able to keep the roof down. But that's how you can use the Bernoulli equation. Just these 3 terms at 2 different places need to be add up to the same thing. And then often what you'll find out is depending on whether something's moving or not, you may get to ignore some of the terms, or in this case, we said that we basically ignored the pressure difference due to being a few feet higher in the atmosphere than in saying that that's going to make not really going to make a difference, just being just above and just below the roof.